Integration by parts is a method of integration that is based upon the product rule. So let's review the product rule. I have two functions. I'm going to call them f and g, but f goes by the name of u as well, and g by the name of v. And the product rule, you all remember, says that when you take the derivative of f times g, it's f prime g plus f g prime. Replacing them with their alter egos, f becomes u and g becomes v. We end up with u, or v, times du dx plus u times dv dx. Well, our quest is to find antiderivatives. So let's take the antiderivative of both sides here. And when we do that, we'll end up with on the right side, v du dx plus u dv dx. Okay. Well, of course, the reason we do antiderivatives is because we're trying to find a function whose derivative is equal to a given function. Well, this left side is saying, find me a function whose derivative is equal to the derivative of u times v. If that was confusing, it is. Well, what that means is it's really just u times v. On the right side, we can kind of imagine, quote unquote, that we distribute the dx through. Du and dx there, the dx would kind of cancel. The same thing happens here. And so we end up with this, the integral of v times du plus the integral of u times dv. And so if we solve this for the integral of u dv for some reason, the integral of u dv is, we don't need that extra parenthesis there, is equal to u times v minus the integral of v times du. So this is what's known as the integration by parts formula. And what you want to do is you want to look at this and you want to note that we start off with essentially something that is just an ordinary function and something that's a derivative. In the end, we replace it by something, and then minus a new integral that is the original function whose derivative was inside the integral, multiplied by the derivative of the original function that was in the integral. And so it's a way of replacing one function by its derivative and another function by its antiderivative. And so it has some very particular good uses. We have the formula there. So here are three scenarios that are common for integration by parts. There are some others, but these are the three most common scenarios. The first one didn't fit on one line, but it's a polynomial multiplied by either the sine of x, cosine of x, or e to the x. That's kind of a typical one. And the reason this works is because the sine, cosine, and e to the x all have antiderivatives or derivatives that kind of cycle through a list of functions. Whereas a polynomial, when you start taking derivatives of it and then higher order derivatives, the powers come down. So your choice for u is going to be the polynomial, and then dv will be whatever trig function or exponential function you had times dx. Another situation is when you have some function, it can be a kind of a wild function perhaps, multiplied by an inverse function. Actually, the inverse of a trig function or an exponential function. So if you have the natural log in an integral, the inverse sine in an integral, or the inverse tangent in an integral, chances are, but not necessarily, that you may need integration by parts. Now, remember, we choose one function that we're going to differentiate. We're going to choose another function to integrate. I don't know the antiderivative of any of the three functions, inverse functions listed here. So I'll let u be one of those inverse functions, and then dv is going to be the other function that's there. And then this last one is kind of obnoxious, really. You have e to the ax, which if you take its derivative, you'll see itself appear again. Same for the antiderivative. You have cosine of bx and sine of bx, whose derivatives and antiderivatives, again, cycle through a list of functions. Turns out you can choose u to be either of the two functions, and then dv will be the rest of the integrand. So here's how we do this. We're going to choose a factor to be the value of u. Everything else, including the dx, will be the dv part. We're going to differentiate u and integrate dv. We apply the formula, and then we evaluate our new integral. As we go through these, I'll explain what it is that makes me believe I'm going to need integration by parts. So the first one I have x times e to the 4x. If the x were not there, if that weren't there, if I were doing the antiderivative of e to the 4x, it would be a rather straightforward integral. But the x is there, it's kind of in the way, and it's a polynomial. Polynomials disappear when you take their derivatives. So that's why we're going to choose, for x, we're going to choose that to be u, and then the dv is going to be everything else, e to the 4x dx. When I do what I need to do, the derivative of u is just 1 times dx, or I would usually just write du equals dx. V, on the other hand, we're going to integrate both sides of this equation. Well, the antiderivative of dv is just v, and we have to remember how to do this one. You could use substitution, but I discussed in my other video about this linear arguments method. E to the 4x, the exponent is where the variable usually is, e to the x. And because I've replaced x by 4x, we have to compensate for that 4 by multiplying by 1/4. And you can check it out. If you take the derivative of this expression, it would be 1/4 e to the 4x multiplied by the derivative of the exponent, which is just 4. And the 4 and the 1/4 would cancel. And so here's how I like to view this. I generally organize it like so, and let me just erase this little bit here. I'm going to erase this guy here. Whoops, maybe I will, maybe I won't. There we go. Usually that's not there. And so, in order to do my formula, it's going to be u times v minus the integral of v times du. So they kind of crisscross there. So this is uv minus the integral of v du. Now, this does pose a problem. We have a new antiderivative to find, but we'll be able to do it. So u, we said, was just simply x. V is 1/4 e to the 4x. And then we subtract, we're going to do the integral of v, which again is 1/4 e to the 4x, multiplied by du, which is dx. So you need to keep those dx's there. There's a history of students not doing that, so keep those there. Because they're, no pun intended, they're an integral part of integrals. Now the first part we can just rewrite. That's just 1/4 x e to the 4x. And then over here, the 1/4 is just a constant, so it can come out in front of the integral. And then, ignoring that 1/4 that's there because we factored it out, we're going to take the antiderivative of e to the 4x, which is, once again, 1/4 e to the 4x. And we'll add our constant. So our final answer is 1/4 x e to the 4x minus 1/16 e to the 4x plus c. One of the common mistakes I see with my students, so watch out for this, is that when they do the antiderivative the second time, they've got the 1/4 there, they sometimes forget that they need an extra 1/4 when they do the antiderivative the second time. For our next example, we've got another one where we've got a polynomial here multiplied by the sine function. So the sine is that cyclic derivative, or integral, which we'll actually be doing, the cyclic antiderivative. And then this business over here is a polynomial whose derivatives will eventually go away if we take them enough. So I'm going to let u be equal to the x squared plus x. And then dv is the sine of x dx. Again, incorporate that dx that's there. I'm going to do the v first since I'm over here. We need a function whose derivative is the sine. I'm tempted to say it's just the cosine, but it's actually the opposite of the cosine. And now for du, we're going to take the derivative. Du will be 2x plus 1 multiplied by dx. And notice I put parentheses in there. Those are crucial because the dx is really a factor of both the 2x and the 1. It's time to use our formula. It is u times v minus the integral of v du. So our u, we said, was x squared plus x. V is negative cosine of x. Now make sure you put parentheses around that, otherwise it's going to look like minus cosine of x. Then we're going to subtract. We want the integral of v, which is negative cosine of x. Wrong color there. There we go, negative cosine of x, times du, which is 2x plus 1 dx. Okay, now these two negatives together can be made into a positive, so we'll go ahead and do that. But we're now faced with a new integral, and once again we have a trigonometric function multiplied by a polynomial, so unfortunately we're going to have to use integration by parts a second time. Ugh. So here's the thing. Since we started off by letting the trigonometric function be the thing that was integrated, the v, we want to keep that pattern. Otherwise, we'll end up back where we started, and you'll get an answer of, well, you'll get an answer of your original expression, which isn't terribly enlightening. Okay, so now I'm going to make things a little bit confusing here with colors, but I know we shouldn't use the same variable twice, but I have kind of released all of this back into the variable land, and I can use those as variables again. So I'm going to let u be the thing we differentiate, the 2x plus 1. dv is going to be the cosine of x dx. Put the dx in there. V will be the sine, because remember the derivative of the sine is the cosine. And then du is a little bit simpler now. It's just a constant, which is a good thing because that means we're going to be done with integration by parts for this problem. So let's put everything back in. I'll bring the negative out front, negative x squared plus x cosine of x. And then over here, I'm going to replace this integral by all the mess that's over here. So u times v, so u was 2x plus 1, might be running out of room here, times the sine of x, but the sine of x, of course, should be in blue, minus the integral of v, which is the sine of x, times du, which is 2 dx. Let's put a little border wall up there. Okay. So we have just a little bit left to go. So we're going to have the minus x squared plus x cosine of x. In here we've got plus the quantity 2x plus 1 sine of x. And then, finally, at the very end, we have really just 2 times the sine of x subtracted. We need a function whose derivative is the sine. Well, that would be negative cosine, and since I have the negative there, let's just incorporate that. So this is going to be plus 2 times the cosine of x plus c. And if you want, you can do a little fancy footwork here and factor out the cosine that's there, and it would become, I guess we would have 2 minus x squared minus x cosine of x plus the quantity of 2x plus 1 sine of x plus c. A little sloppy there. Okay, now let's look at the next one. Oh, it looks terrible. It looks horrible. But let's think about this very carefully. I've got a function whose argument has been replaced. Like up here I had the sine of x. Even sine of 3x wouldn't be too bad. But here I have sine of e to the x. And that really is troublesome for me. And so I think I might be using substitution. I think about what the derivative of e to the x is. Well, it is e to the x. Oh, it's not e to the 2x. So something strange is happening here. So let's think about how we can produce e to the 2x from some algebraic maneuver. E to the 2x is actually, you can look at it in one of two ways. It's either e to the x, that quantity squared, or e to the x times e to the x. I'm going to use the second one that I said there. So this is going to be the integral of 10 e to the x times e to the x sine of e to the x dx. Okay, now you might say, well, that doesn't seem very enlightening. if I make a substitution, I would let my substituting variable be e to the x. Its derivative is e to the x. So the sort of du part of it all would be maybe one of these e to the x's. Well, then what do I do with the other? Well, fortunately, e to the x is kind of a funny function. Its derivative is itself. So we had said we're going to let whatever our variable be this e to the x, and we'll let that variable also be, that e to the x be whatever variable we choose. I'm going to choose t. And the only reason I'm choosing t is because if I choose u again, I am so accustomed to the uv minus integral v du that I can do it, but it's not comfortable for me to do that using a different variable. So I'm going to let t be equal to e to the x. Then dt is e to the x dx. So just to show you what I'm doing here, I'm going to move a couple things around. We have 10 e to the x. I'm going to take this second e to the x, you can tell it's the second one, of course, and move it so it's grouped together with the dx that's over there. Now, e to the x dx, we said was equal to dt. So that guy is going to be replaced by dt. And then let's see what's going to happen here. Well, I chose t because it was the argument of the sine, so that's going to be the sine of t. And then I have this extra e to the x out in front. Let's call that guy t also. So t, and then I have 10t sine of t. So I look at this, and I've got a new integral, and I say, hey, look, there's that t that's in the way of us being able to evaluate this without it. 10 sine of t, I know it's antiderivative, but the t is in the way, so I'm going to let u be the 10t that's there. And then dv will be everything else, sine of t dt. du is 10 dt, and v will be a function whose derivative is the sine, which is the cosine, but with a negative in front. And so now we do that little crisscross business, uv minus the integral of v du. Okay, so u, we said, was 10t. And then the minus cosine, I'm going to put the minus out front here, minus the cosine of t. And then we're supposed to subtract the integral of v times du. Well, our du is 10 dt. I'll put that at the back end. Sometimes I'll just pull that 10 out front, but I didn't here. And v was negative cosine, so there's the cosine there, and then there's a negative, so that'll become a positive. I like to circle signs when I change them just so I know I've done something. And now we're ready to finish this off. This will become negative 10t cosine. Oh, I wrote the wrong variable there. That should be a t, and that should be a t, and over here that should be a t. Okay, so 10t cosine of t plus the antiderivative of 10 cosine t, the function whose derivative is the cosine is the sine of t, and then plus a constant. So one of the things you'll find is you might need to make an initial substitution before doing these integration by parts problems. Okay, now let's look at this crazy guy. We've got x times the inverse tangent of x dx. One of the types of integrals that I suggested that you might encounter are ones where you have a logarithm, an inverse sine, or an inverse tangent. Well, here's one with an inverse tangent. Now, what I would actually first do if I were doing problem solving with these things, because this could happen, is I would look to see if the derivative of the inverse tangent is involved in the integrand. The derivative of the inverse tangent is 1 over x squared. Keep that in mind. So it's not here, so I think that integration by parts is going to be what I want to do. Now remember, we want to choose one thing that we differentiate and one that we integrate. So I'm either going to differentiate inverse sine of x or inverse tangent of x, or I'm going to differentiate the inverse tangent of x. Well, I don't know what the antiderivative is of the inverse tangent, so I'm going to use u as the inverse tangent of x. And then dv will be everything else, x dx. This is actually a definite integral, so we'll see a little bit different stuff that's going on here. V then, if dv is x dx, v is the antiderivative. I was tempted just now to say it's equal to 1, but it's not. It's actually 1/2 x squared. And then du is going to be 1 over 1 plus x squared dx. And so we'll get u times v. So the inverse tangent of x multiplied by 1/2 of x squared. I don't typically like to do that. I like to put my x squareds out front, but that's okay. We're going to evaluate that from 0 to 1, and then we're going to subtract the integral of v times du. Now this time I am going to pull the 1/2 out front. So let me erase that really quickly. I'm going to pull the 1/2 out front. And I want the integral of x squared, that's the v, times du. This is a strange one. X squared, I'll put in the numerator, and then the 1 plus x squared I'll put in the denominator, and we have a dx there. Okay. And we want to do this as a definite integral from 0 to 1. Now, let's evaluate this first piece. I'm going to delay some nastiness here. 1/2, when x is equal to 1, we're going to get 1 squared. We want the inverse tangent of 1, and then minus 1/2. Oh, okay, this was a waste of my space. 0 squared times the inverse tangent of 0. All right. Now we've done minus 1/2. The way we would handle this guy, there are multiple ways we could do it, actually. One way would be, one way would be to use long division. And long division will do exactly what we need it to do. Now, I'm going to do it kind of the same. I'm going to really kind of use long division, but I'm going to be sneaky about it. I see I have x squared in the numerator. I have 1 plus x squared in the denominator. They're almost equal. Had they been equal, I would have been able to just go ahead and divide them. Well, what would make them equal? What would make them equal, and I'm going to do the manipulation here in the numerator, would be to add 1 to the x squared that's in the numerator. Okay? So I'm going to do that, and I'm actually going to write a false statement initially here. Okay? You can't just add 1 to an exponent, but if you add 1 and subtract 1, you can do that. And so now this becomes 1/2. The inverse tangent of 1 is pi over 4. This term is all 0, minus 1/2. We're going to do the integral from 0 to 1. And then when I split this up, it'll be 1 plus x squared over 1 plus x squared minus 1 over 1 plus x squared dx. Okay. This is equal to 1. And so I'm just going to go ahead and take the antiderivative. 1/2 of pi over 4 is going to be pi over 8 minus the 1/2. We're going to put parentheses in there. The antiderivative of 1 is just x. The antiderivative of 1 over 1 plus x squared is the inverse tangent of x. And we want to evaluate this from 0 to 1. And so we get pi over 8 minus 1/2 of x. Oops, well, we're supposed to replace x by something, aren't we? Let's do that. X is equal to 1 minus the inverse tangent of 1. And then we will subtract, okay, 0. Oh, that's not really important. The inverse tangent of 0. Don't assume that functions evaluated at 0 will always be 0. In this case, it is, but that's okay. And so, let's see here. We have pi over 8. I'm going to write up here just a little bit. Pi over 8 minus 1/2 of 1 minus, with the inverse tangent of 1 is pi over 4. And then all of this is equal to 0. And so this ends up being, when you combine this, you'll have a plus pi over 8. Well, you'll then have 2 pi over 8, which becomes pi over 4 minus 1/2. All right, for the next one, again, I see an argument has been replaced. E to the x is become e to the x to the 5th. Well, that doesn't feel too good. So I'm tempted to let u be equal to the exponent, x to the 5th. Substitution would say, okay, well, the derivative, look for the derivative of that, that would be 5x to the 4th. I have an x to the 9th there. That doesn't do me any good. So what I'm going to do is say, well, x to the 9th is 9 factors of x. For du, I needed 4 factors of x, or for my substitution, I would need 4 factors. So let's pull off 4 of those factors. This is the integral of x to the 4th. Well, you know what? Let's not even put that there. Let's put what's left over. If I pull off x to the 4th, I'm left with x to the 5th, e to the x to the 5th. I'm going to put the x to the 4th dx together because the derivative of x to the 5th involves x to the 4th. So involves x to the 4th. So that's what I'm going to do there. So I'm going to make a substitution here. I'm going to let t, just like we did before, be x to the 5th. Then dt is 5x to the 4th dx. Well, I don't have a 5 there with the x to the 4th, and so the way we got around that was to multiply both sides of this by 1/5. 1/5 dt is x to the 4th dx. And here we go. So when I make my substitution, I'm going to pull the 1/5 out front. And then x to the 5th is t. E to the x to the 5th becomes e to the t. And we already said x to the 4th dx is 1/5, which we have out front, x to the 1/5 dt. And now I recognize an integration by substitution problem again. E to the t, if you take its derivative, if you take the derivative again, if you keep doing it, you end up back with e to the t. The t is in the way. If it weren't there, the antiderivative would just be e to the t. So I'm going to let u be equal to t, and then I'll let dv be e to the t dt. That means that v is e to the t, and du is simply dt. Oh, this is kind of a nice one, really. Be careful, you've got a 1/5 out front, so you need parentheses, or I'm putting in brackets. Then we're going to have uv. Well, u is t, v is e to the t, minus the integral of v du, that's e to the t dt. And now we go ahead and we integrate e to the t dt. We get 1/5 t e to the t minus e to the t plus a constant. And I thought I forgot the constant on the previous problem. I didn't. And we need to remember that t isn't just t. It is a representation for x to the 5th. So my final answer is 1/5 of x to the 5th e to the x to the 5th minus e to the x to the 5th plus c. Okay, next. Here comes one of the nasty ones, okay? It just is kind of, it's really, in a sense, circular. You'll see what I mean. And it just takes a little bit of time and a little bit of creativity as well. In the end, it doesn't feel like we're done with the problem. This is one of those cases where each factor, e to the 4x and cosine of 5x, each factor is some sort of function whose derivatives or antiderivatives cycle through a bunch of them. So we can choose them any way we want. I'm going to choose, I like taking derivatives of trig functions better than I like doing their antiderivatives. That's just personal preference. So I'm going to let u be equal to the cosine of 5x. Then dv is going to be, I usually do these in blue, is going to be e to the 4x dx. So v, v is e to the 4x, so its antiderivative would also involve e to the 4x, but I need to compensate for the 4 by multiplying by 1/4 out front. It's kind of the opposite of what we're going to do with the cosine. Du, the derivative of the cosine, is negative sine of 5x, but the derivative of 5x is 5. We multiply by 5, and for that same reason, we are going to divide by 4 over there. This is going to just be a mess of fractions, folks. Okay, so we're going to have v times du, or u times dv. I'm going to put the number out front. 1/4 cosine of 5x e to the 4x minus, I'm going to take all constants, the negative 5 and the 1/4, and bring them out front. But because the 5 is negative, I'm going to actually be adding 5 times 1/4 is 5/4, and then I put all this business together. E to the 4x v times du, e to the 4x sine of 5x dx. We always end up with a new integral when we do integration by parts. My new integral is similar to the integral I had before. Since I started by letting u be equal to the function, the trig function, I'm going to continue letting u be the trig function. So it's going to be the sine of 5x. Du then is 5 times the cosine of 5x. And dv will be everything else. That's the e to the 4x. Does this sound familiar? dx. V is 1/4 e to the 4x. Okay, so this should be equality here. This is equal to 1/4 cosine of 5x e to the 4x plus 5/4 times, we're replacing the integral by u times v, which I'm going to have a 1/4 again, 1/4 e to the 4x sine of 5x minus the integral of v times du. Now remember, v and du each have numbers. 5/4, it's being to get a little messy there, 5/4 integral of what? Integral of v times du is e to the 4x cosine of 5x dx. And I'm running out of room there. Got to end my parentheses. There we go. Okay. Now, this seems kind of futile, and it also seems kind of messy. So let's simplify things. I'm going to bring this e to the 4x out front. I get 1/4 e to the 4x cosine of 5x. I'm missing the x there. I'm going to distribute the 5/4 to each of those terms before I do anything about the integral. So that's going to be 5 plus 5/16 of e to the 4x sine of 5x. And then, minus 25/16 of the integral of e to the 4x cosine of 5x dx. Now, at this point, you're probably saying this is never going to end. And you could be kind of correct there. It would not end if we don't make some sort of observation, which we're about to make right now. Notice that the integral that we have now that's an eraser. Learning this. Here we go. The integral that we have now is the same as the integral that we started with. Okay? So we can treat this like an equation. Well, we can't, it is an equation, so of course we can treat it like an equation. We're going to add 25/16 of my integral to both sides. Then we're going to do a little bit of algebra. So we will have the original integral of e to the 4x cosine of 5x dx plus 25/16 of that integral e to the 4x cosine 5x. It's equal to everything that was not highlighted. So the 1/4 e to the 4x cosine 5x plus 5/16 e to the 4x sine 5x. We have two integrals on the left side. We have 25/16 of the integral on the second term. In the first term, we can treat it as we have 16/16 of that. So that means we have 41/16 of the integral. I'm not going to write all this out. We have 41/16 of the integral equals all of this nonsense over here. And so all we need to do is we need to multiply both sides by 6/14. And we'll end up with the integral of e to the 4x cosine of 5x dx is equal to 16/41 of everything that was on the right side. 1/4 e to the 4x cosine of 5x plus 5/16 e to the 4x sine of 5x. And you can see that when we simplify, we end up with 4/41 of e to the 4x cosine 5x plus 5/41 e to the 4x sine of 5x. So you can generalize this. And in order to generalize it, you might want to think about where does that 41 come from. For our last example, I'm going to throw in, and it doesn't quite feel like any of the types that we've talked about before. I'm going to rewrite this last one as the integral of x times 1 plus 4x to the negative 3 dx. Now, there is a sense in which it does feel like one of our previous ones. If this x were not there, I could go ahead and maybe use a substitution. Now, this substitution is really nice because the derivative of 1 plus 4x is just a constant 4. And when you do your solving for du, you would multiply by 1/4. So there are faster ways to do it than using substitution. But the x is kind of in the way. And so I'm going to use integration by parts. I'm going to let u be equal to x. I'm going to let dv be equal to 1 plus 4x to the negative 3 dx. So du will be dx. And then v, if we do things carefully, the new exponent is going to be one more than the old one. So that's going to be 1 plus 4x to the negative 2. We need to multiply by negative 1/2 out front because of the division by the new exponent. And because the derivative, because the inside is a linear function and its derivative is 4, we need to multiply by 1/4 as well. We're going to do our little multiplication business here and multiply those. And so we have, let's see, u times v. Ooh, v got kind of nasty on me, so it's negative 1/8. U is x. And then I have 1 plus 4x to the negative 2 minus the integral of v times du, which will go back and forth here. I've got a 1/8 that I can pull out, but it's negative 1/8, so I'm going to make it plus 1/8 times the integral. V is just 1 plus 4x to the negative 2 dx. And then we can use the same method to evaluate this final integral here. And so we end up with negative 1/8 x times 1 plus 4x to the negative 2 plus 1/8. My new exponent here will be 1 plus 4x to the negative 1. So I need to multiply by negative 1, which is the same as dividing by negative 1, and then plus a constant. And if we want to make things look like they kind of did at the beginning, it would be x divided by 8 times 1 plus 4x squared minus, and there should be a negative there as well, 1/2 times 1 plus 4x plus a constant. If you want an extra little challenge, try to solve this same problem, part G, using substitution only.